Hi, how you doing? My name's Phil Winder and I'm the CEO of Winder.ai. If you don't know already, we are an AI consultancy. We help companies with AI consulting and AI development projects. If you're interested in any of those services, then please check out our website. So today I'm going to talk about a presentation that I gave at Go to Copenhagen about a month ago. We're going to dig into some of the specifics of fine-tuning and training LLMs. It's quite a long presentation. It's going to take approximately, about hopefully 45 minutes. I'm going to rattle through the slides to get to a quite hilarious demo. I recommend that you hang around for the demo because it's quite funny and quite embarrassing, and they're often the best demos. So yeah, hang around for that. And throughout the presentation, if you've got any questions, then use the chat functionality in LinkedIn, the comments, or in YouTube, for example, and they should pop up on my screen and I should be able to see them. I generally do all of the questions at the end, but if I do notice anything that's pertinent at the time, then I'll try and answer it there and then. Okay, without further ado, let's crack on. So this is the presentation, how to train an enterprise AI assistant from scratch. So just a quick caveat on the title of this presentation. So obviously the titles and abstracts have to be written a year before the presentation is actually written, or maybe not a year, but 6 months. So this presentation is, the title should be more like how to fine tune an AI assistant on some example data. I'm not really going to talk about deployment or any of the associated aspects with regards to LLMs. And so, you could say that there's maybe less enterprisey kind of concerns within here, but still it should give you some foundations and help explain what LLMs are and so on and so forth. Just before we move on, bear in mind that a lot of my presentations have Hitchhiker's Guide quotes because there's so many quotes in there that are totally relevant to a lot of the work that we do. This time, this is the quote from Restaurant at the End of the Universe, where he's talking about if you're ever looking to earn some easy money, then you can spend some time being a counselor or a psychiatrist in neurotic elevators. And that's going to be definitely relevant later on. So the structure of the presentation, 7 sections, and the first section I'm going to talk about the history and then the theory of LLMs. So basically what came before LLMs, why it's not necessarily new, and then I'm going to dig into how they work and some of the architectures. Then I'm going to talk about the data and training aspects of the LLMs and how it's actually incredibly difficult to train your own LLM. And this really sets up the premise of fine-tuning. And so I'm going to talk about fine-tuning a lot here and how you do it. Then a little bit on deployment. This isn't really a deployment talk anymore, actually. But so just a few kind of notes to basically say that there's more information here. And and then the embarrassing demo at the end. And looking forward to that. It went really well last time. No idea what it's going to do today because, this is all generating on the spot, live demos. You never know what might go wrong. Okay, so let's have a quick discussion about the brief history of LLMs. What is an LLM? Let's get this clear and straight from the beginning. A large language model, or LLM for short, is an AI model. It's a machine learning model that is trained using supervised learning on a large text-based data set. It's then refined using reinforcement learning using user feedback, where what I mean by that is basically users read the outputs and read the responses of these things. And then they use the preferences of those users to basically control and refine how well that model is, to refine the actual, the underlying model to generate better text. And ultimately, all these models are trying to do is to predict the next word. All LLMs everywhere can be decomposed into the central premise or the central idea that it is a machine learning model that predicts the next word in a sentence. The reason why they're so intelligent is because there's a lot of context involved in that generation, and so it can sound like human-like and lifelike. Okay. There's a long history of machines that do this kind of thing, and one of the earliest ones that I could sort of vaguely remember. It came around in like the 60s, I think. But even when I sort of started my sort of electronics career about 20, 30 years ago, there were still mentions of this piece of software called ELIZA, which was even advertised as the artificial intelligence simulation, which is great. And basically, it was just a set of heuristics that effectively asked questions, like pre-scripted questions about things that you wrote about, but it sounded, really smart and really intelligent. You can go to elizabot.js and actually try this out yourself. It's really cool. So that was 1966. Yeah, I was nearly there. So that's a really long time ago, where people started to talk about AI and the use of AI to communicate with people. But really, the watershed moment was in 2013, when the Word2Vec paper introduced the idea of embeddings. And this is the idea where you can take a piece of text and convert it into a number representing that text. But the cool thing is about that is that you can learn how best to do that conversion. And eventually you can do things like addition and subtraction in embedding state, in embedding space, because they're just numbers, and translate them back to words again. Then there was a couple of refinements and improvements to the machine learning models that existed at the time. And it was really the modeling of text as a sequence of tokens, which made it easier to predict the next token. And that's really where the idea of generation of a generative text-based AI came from. Transformers and BERT and GPT-1 all improved how the model was looking at that text in order to provide better predictions, basically. And then GPT-2 and GPT-3, 2019, 2020, basically all about scale, just bigger data sets, bigger models, and they got better and better. And then in late 2022, the ChatGPT interface kind of came out. And that was at the point where I didn't have to explain what I did anymore. I've been doing machine learning, data science, AI for the best part of 15 years now. And for the first time in my life last year, I didn't have to explain what AI meant and what it is. So that's great. In terms of how an LLM model works, well, it's actually quite interesting to step back a little bit and actually talk about how they're built. This comes from the Instruct GPT paper. Let's get rid of my face for a second. My apologies. When I removed my face, I kept talking, but it muted my microphone. Let's start that again. Apologies, everybody. Thank you, Jonathan, for letting me know. I'm glad I left Slack on. So starting again, this is from the Instructs GPT paper, and this describes how they trained a large language model. You first start with a huge corpus of text data. That could be scraped from the web. It could be scraped from books. Either way, you need a huge corpus of data, and then you're training a model to predict the next word in a supervised way, or not necessarily next word, but you can think of it as like that. And the idea here is that if you imagine you've got a poem, a sentence, for example, you chop it in half and then say, predict the next word. And it will predict the next word, and it will either be right or wrong. If it's wrong, then you can nudge the parameters or the weights of that model in such a way to make it more likely to generate the correct result next time. Okay, so that's supervised learning. Then the second step is to start collecting comparison data. And offering that out to real humans and say, well, what's the best generation? What's good here? And that's a really interesting step because it allows you to apply like safety or guidelines or ethics or ideas. Things like if it's generating some really bad things, you can say, no, that's a bad example. I don't want that. I prefer the good one. And then a reward model, which is another secondary machine learning model, is trained to predict what people would, in general, how they would score a particular output. And then that reward model is then used in reinforcement learning to refine and further improve the underlying large language model. Okay. So now let's talk a little bit about, let me just skip a little bit. Yeah, so now let's talk a little bit about the architecture of some of these systems. And this was one of the first ones. This is from 2017. This is the transformer architecture. It's now quite famous in the LLM world. It consists of two main halves, I guess you could say. The first half is an input side, and the second half is the output side. They both contain shared components, but they're doing different jobs. The left-hand half is attempting to take some raw text and convert it into basically a higher dimensional space. You know, these idea of converting it to the embeddings and then converting it through into parameters that the model can use to model higher level concepts. And then the right hand is taking a question or a prompt and is attempting to provide an answer based upon the information in the context. Okay, let's dive into the right hand side a little bit now, because the right hand side is so the transformer architecture came in BERT, but people realized that actually all we need is the right-hand part. We're just trying to generate text here, and we can just feed in everything, the input, the context, the questions, everything into the input of the so-called output stage. So from GPT onwards, they're only using the right-hand side of the transformer architecture. And the first step there is to tokenize the embeddings. So there's two steps here. First is tokenization, and that's the process of going from text, like full-on English text or Spanish text or whatever, into tokens. And you can do that in many ways. A simple a token could be a specific word, or it could be a subword, or it could be a letter, or it could be an ASCII code. It could be lots of different things. But most people have now standardized on using like subword sequences so that they can capture a large number of words with only a limited number of subword sequences, subword tokens, sorry. And then the embedding part is this idea of taking that token and then converting it, or series of tokens, and converting it into this high dimensional embedding space. The next part is inside this block here, and it's mass multi-head attention, addition, and normalization and things. Basically, this step is attempting to figure out the probability of how important each of those tokens are to the output. And the reason for doing that is that we only really want to forward and pass forward to the subsequent layers only the important bits. Okay. And how they actually establish that probability is through backpropagation. So based upon the answer, it's like, oh, actually, that individual token was really crucial in the answer. Then we've got a bog standard normal multi-layer perceptron, a normal standard layer in a deep learning model to predict what the next token is. And then we just make it deep, as in all deep learning. Like, it doesn't have to be complicated, just add loads of layers, and that adds the complexity in. And then finally, we just do some softmax and some basically picking what the final prediction should be given this list of potential solutions. Okay, and that's it. And that's GPT-3 in a nutshell. So that's only about a year old, and you can see how well it performs. It's a relatively simple architecture, scales well in the sense that there's lots of duplicated parts of the architecture there. But really the crucial idea here is that there's just a huge amount of data, and a huge amount of training time and many of these deep blocks to provide the complexity. Okay, talked about the reward. Right, okay. So now let's talk a little bit about why we actually want to build a reward model in the first place. So there's three reasons for doing this. Alignment is the idea of attempting to make the language model do what it's supposed to do. And then we've got safety, which is fairly self-explanatory. We're trying to ensure that the outputs of the model are safe and again doing what it should do. And then finally is quality control, and I've got a good example of quality control here. This is a website that I just happened to stumble across when I was searching for some InstructGPT stuff. I think I was just looking for the paper, and I saw this. I thought, I'll have a quick read of that. And it's like, fair enough. But you can see that this web page in itself has been written by ChatGPT. You can see, 3/4 of the way down the page there, it's continue writing, please, ChatGPT. So it's obviously being used there. And the reason why quality control is important is because remember that the current ChatGPT models are trained on a huge crawl of the internet. And so this data is probably unlikely to have made it into the final data set. But it is quite conceivable that this website was used as training data in the future versions of ChatGPT. And so you can imagine that if it just sees its own rubbish writing, it can, start to want to predict rubbish writing again. But another thing that I noticed on this website is that they attempted to apply some DMCA like mark to say, please do not copy this website, even though they've obviously used the copied content in their own web post. And also it also highlights some of the I guess some of the dangers, some of the worries and some of the less some of the things that you've got to be a bit careful of when you're working with this technology. You can see the potential avenues for abuse, basically. So, just be good. All right. And then we've got the reinforcement learning. And obviously, if you're not an expert on reinforcement learning, I'll just give you a quick overview. So the reinforcement learning is used in the sense of attempting to use the reward model that we've trained to retrain the base LLM, which is then making new generations. And there's then a couple of options again. So we maybe generate 2 options, and then the model will again predict which of those are the best and provide another value, which is fed into the LLM again, so on and so forth. And that goes around in a loop, trying to improve the underlying model according to the defined rewards there. And in RL terminology, then we have the observation is the initial prompt, the prompt that's currently under test. You might cycle through lots of different prompts here, maybe from a test set or something. The policy is the base LLM. That is the thing that is actually taking the observation and generating the actions. The actions are the generated output, the text that is being generated. The reward model is part of the environment. That's the thing that's providing the agent the reward. And then finally, that reward is fed back into the policy again. So standard reinforcement learning stuff. If you're interested in that, then definitely check out my book on reinforcement learning by Riley. The website is rlbook.com. Okay, one of the most important aspects is the data, as always. Anything AI, anything machine learning, the most gains, the best performance, the most crucial aspect is always the data. There's a couple of arguments within these papers that are basically arguing certain things. The first argument for fine-tuning is that massive data, it turns out that using massive amounts of data is better than using your own data. So you might have this idea of training your own LLM on your own subset of data. Maybe it's proprietary or something like that. The challenge with that is that in general, huge data models that have been trained on huge data sets will outperform your model that has been trained on a small subset of your proprietary data. So that's okay, but it also adds a problem. Well, what happens if we have some data, some proprietary data, some specialist terminology that hasn't made it into that original model? Well, it turns out that the combination of the massive data, the foundation models, the large language models that have been trained on the massive data, and then adding your own data over the top in a number of different ways provides better domain specific performance than the large language model alone. So I think that's quite intuitive. I think, yeah, there's nothing extraordinary there. It makes sense. Um, However, there's lots of caveats with all of this, and one of the main ones is that the curation of that data is really, really hard. Um, yeah, it's labor intensive, and I think actually, do I? Oh no, I say it next. It's labor intensive and it's quite hard to manage. There's a theory called no free lunch, which states that there's no one algorithm, there's no one machine learning architecture that is best for all possible problems. So everybody just throws deep learning at all problems now, but the no free lunch theorem proves that no single architecture is best for all applications, and it's the same for for when you're trying to clean data as well. So you can't rely on one single special data cleaning algorithm or software or technique because it's never the best for all situations. Don't rely. Actually, I've changed my mind a little bit on this statement. It's not don't use magic data cleaners, just don't rely on magic data cleaners because you will have domain specific problems that will require some specialist knowledge, expertise, or tooling in order to clean your data. There are a lot of libraries out there that can help you along the way, but they're not the peak of performance. Okay. One interesting result I found recently was that, and in fact, it's the model that I'm going to show later on, is this Falcon models, the Falcon set of models. There's actually basically no difference in architecture, in the underlying algorithmic architecture of the model. The only difference in their LLM is that they cleaned the data better. And when I say clean data here, you might think they did something really fancy. No, they just did stuff like deduplicated and removed the lorem ipsums and things like that. Just cleaning out the data. But also there's also some evidence to suggest. Oh yeah, no, in fact, yeah, I've already mentioned that. But when it does, come to cleaning that, human insight is still the best. There's a paper here that attempts to prove that especially a domain-specific expert cleaning the data can do it better than any current algorithms that exist today. So yeah, once again, it's just hard, laborious work, but it does pay off. Another one was talking about the tokenizer as well. Don't forget about the tokenizer. It's trained upon this massive corpus of data, and it's then packaged with the model typically. But if you have a very highly technical domain, if you're working in an engineering domain, for example, there might be words that aren't well represented by that corpus of data or in the tokenizer itself. It might not be able to even tokenize specific words properly. So you might want to look at adding things to the tokenizer. But in this paper themselves, they tried to prove that adding changing the tokenizer for clinical healthcare settings improved the performance. They kind of like missed the elephant in the room, which these results are showing like various LLMs, LLM Llama 2, LLM blah, 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 trying to prove that their tokenizer is better. But they're kind of missing the point that the logistic regression model, the non-deep learning, non-LLM, the super simple, most basic model that you can pick in your machine learning toolbox is almost as good as all of the LLMs. So this is just a bit of a warning, really, just to watch out for over engineering here. Typically, we're building products, we're building solutions, and they take time. If there's a simple solution that will eventually be more robust, then pick that. Don't use an LLM. So what does the training data look like? So you'll see different forms of data. you'll see lots of raw text like data sets, big web crawls and things like that. You'll also see lots of data sets that are formatted for supervised fine tuning for the specific task that the model is being asked to do. So it could be like a prompt and an answer, or it could be a context and a question, or it could just be a dialogue flow, for example, multiple questions over time. And then finally, we've got the reinforcement learning data that's performed at the output. That's quite useful for improving, if you agree with the accepted responses, it's quite useful for improving your own models. So there you'll see the initial prompt or context. You'll see the accepted response and the rejected response. There's a link to a website there from some chap that has collated a lot of these examples together. So if you're looking for a data source, for example, for your LLM, then check out that website. All right, and we'll skip that for now. Right, so let's go back to the architecture again and discuss how we actually train these things. So what parts of the architecture are trainable here? I'm just going to attempt to remove my face again without removing myself. Yeah, so you can see that we've got the architecture there on the left-hand side. And when we, I'll just get rid of that, actually, hide that. You can see all of the boxes in yellow there are all of the trainable parts of this architecture. So all of the bits where we have a set of weights basically sort of buried deep within the maths of the algorithm here. So there's quite a lot to train. And it turns out that when you're adding all of these deep layers, deep, it becomes incredibly expensive to do so. This part in particular, training these deep layers, it costs a significant amount of money. This is, when you hear the stories of these large companies spending tens of millions of pounds, this is where the cost is. It's a large amount of data, a very complicated model. It takes a long time to train and a lot of hardware. So you can fine tune this directly. So technically, what we can do is take those weights, and then we can effectively just nudge the numbers of those weights of a pre-trained model, of a foundation model. I'm going to call it a foundation model from now on. We could take a foundation model and we can just nudge those weights a little bit to perform better on our domain-specific problem. The problem is that there's still billions of parameters there. There's still billions of weights that we need to alter. And so it's slow. It's hard to do because you don't know, like, it's quite hard to say that, well, if I change this weight, how's that going to change another weight? It degrades performance because of that. You might nudge it in one direction, but it turns out that you've, completely wrecked its logical reasoning performance, and also then you've got the usual caveats about size and diversity of data that apply in general ML problems, where you need a data set size that is proportional to the size of your model. And so if we've got billions of parameters, you sure need billions of examples of data. Wouldn't it be great if we didn't have to do that? Now you can. So there's a recent, maybe a couple of years, a year or two old, really, a paper and an implementation from Hugging Face, which attempts to build a little adapter model, a model that sits on the side. I like the word adapter because it kind of fits in with the software definition of the pattern adapter, the adapter pattern, where basically we alter the behavior of the model, not by changing the underlying weights of the foundation model, but just by adding a very small, easily tunable model to the side and then adding that back to the original model. And so you could control the complexity of that adapter. It can be anything from, very simple single layer linear regression style model all the way up to, a complete replica of the original foundation model. But, controlling those parameters, we can basically come up with a compromise that is still capable enough to alter the behavior, but also small enough to actually be trained in a reasonable amount of time with a small amount of data. Okay, so that's great. So now we've got a way of fine-tuning, but we've still got a bit of a problem about these number of weights. There's still billions and billions and billions of these weights, and all of those billions of weights are a number and they need to be represented in memory. So this is an approximate table showing you how much memory you need, how much well, if you're wanting to run this in a GPU, then it's GPU memory. How much GPU RAM you need for each of these models, just to load it in, just to load it up. Okay. The Burton, GPT-2 was just about okay with the current state of the art. But if you look at the bottom now, GPT-3 and God knows what GPT-4 is. There's so many parameters in there that there's no hope of ever fitting these models into a single GPU. So you have to either have multiple GPUs or you have to have virtualized, GPU clusters that allow you to spread these things across them. Either way, that amount of memory is expensive and hard to acquire. So wouldn't it be great if we can squash that down a bit? And you can through quantization. So quantization is the idea of representing a number in a smaller number of logical bits. So this is an example of a sine wave, which looks continuous-ish. And an example of how you would try and encode that sine wave in just 4 bits. So in just two bits, which has 4 states. So there you go. So we can take a float 16 number, which is the representation that's usually used to encode a number in many of these foundation models, and you can squash it down to 2 bits or 4 bits or 8 bits or anything like that. Right, you might be thinking right now, and I won't blame you, that this is all a bit too much. So remember back to the start that you can make easy money and good money just by canceling these neurotic elevators. So it's really important to remember that the LLMs themselves are already highly capable. So you can mess around with the context, mess around with many parts of the model just by altering the prompt, altering the context, and things like that. And you can come up with some really sophisticated applications. This is an example of an application that I came across whilst I was looking for a good example of a prompt, and it's a website called Mr. Reindeer, but spelt a bit wrong.com. And it's basically, I think it's one of the first examples that I've seen of writing code within a prompt to develop an application that runs on top of an LLM. And I think that's quite fascinating. The LLM is almost becoming the runtime, the virtual machine of general purpose, like generative applications. And it performs really well. In particular, this is a prompt that allows you to learn any topic, and it basically acts as a teacher, and it does a really good job of taking you through some example, course-like structure, and that's all done just from the prompt. This is an example that I found from typing in that I'd like to learn about how to fine-tune a large language model. Okay, I'm going to skip a little bit through the deployment section here because there isn't a huge amount of content. It's more just a reminder that there's lots more to think about when you're actually deploying this into production. Couple of things that I'd like to talk about, though, is adversarial attacks. So all models and AI models and all software, for that matter, is open to attack if people really wanted to. But the adversarial attacks, which is the type of an attack which is trying to make the model do what it's not supposed to do purely by altering the prompt. So there's an example on their website, LLMattacks.org, which adds an adversarial suffix to a prompt in order to get around some of these guardrails that you've attempted to instill during the reinforcement learning process. And that's very similar to some work we did previously, which was using reinforcement learning to attack firewalls, web application firewalls. There we were effectively writing an adversarial SQL injection query. So rather than adding it to the prompt, we're adding it to the SQL injection, the query prompt for the SQL, and finding ways of circumventing these things. So this kind of parallels between LLMs and SQL engines, actually. I'll skip through that. Yeah, we'll skip through this. It's just a comment on the safety and the fairness and the bias of these things. And I think what actually the one thing I'd like to talk about here, this is a slide that kind of discusses the differences between normal software and LLMs. And when you're doing development of normal software, it's very reliable, it's consistent, you can test it, it's static, it's got protocols, and so on and so forth. And it's quite easy to control the basically the ethical boundary of a piece of software. With LLMs, it's much harder because the behavior is complex, it's emergent, and it requires some very sophisticated moderation. But one of the most interesting ones is the feedback loops. So I noticed this the other day, and it went around the Twitterverse, and it was a really great example of this in action. So this is Cura, and they've just introduced a new feature which uses ChatGPT to present an answer to a question. And, so the question here is, can you melt an egg? And ChatGPT says that yes, an egg can be melted. The only way the most common way to melt an egg is to heat it using a stove or a microwave. And then the person, the human below it, is saying, no, you're not melting an egg, you're cooking it. It doesn't melt. So anyway, so what happened here is that the problem here is that Cura is like one of the most SEO'd websites on the planet. Like if you type in any question, it's quite likely that Cura's in the top 10 of any particular question that you answer, that you ask. And that means that then it's showed in Google search snippets. So if you go into, well, if you at this point in time, it's probably not there anymore, but in Google, if you typed in can you melt eggs, then Google is scraping Cura, which is scraping the ChatGPT answer and then presenting it as a fact, saying yes, an egg can be melted. But of course, remember back to the beginning that these models are trained on these massive web corpuses from these scrapes of all these websites. So ChatGPT 4 is now learning that yes, you really can melt an egg from a question that it has answered previously. And it's just being reinforced by all of these systems that are attempting to make it easier to use. Okay, you don't get that in software engineering. You don't get that usually in most machine learning problems. To be honest, this is a huge and complicated feedback loop. All right, let's move on to the demo now. I'm going to take you through a couple of examples, or well, an example really of how to fine tune a large language model. So let me try and bring up my screen. Let's just make sure it's working. All right, let me know if there's any problem, by the way. Okay, right. That's the inference one. We'll come to that in just a second. Right, so I've got an example notebook, or a couple of example notebooks here, which you still can't see. There we go. I've got a couple of example notebooks here, which I'm just going to quickly blast through. I think I've got a link to these notebooks at the end. They're just on GitHub, so you can go and take a look yourself. I'm going to use a small model, Falcon 7B, which is a model that can just about run on a single GPU. And I'm then going to use quantization to ensure that it fits on a single GPU. And then I'm going to use the PEFT library, the PEFT library to provide the adapter, so you don't have to fine tune the whole model. The goal of this demo, and now I'm going to start giving you a hint of what this is. Nothing on the screen. That's interesting because it's definitely there. I can see it on mine, Jonathan. Try adding it again. So that's me. You can see me. And then you should be able to see the notebook. I'm fairly sure it's there, Jonathan. Let me know. You see a black screen. Oh, thank you, LinkedIn user. That is problematic. Right, let me try and share like a full screen, a full desktop rather than... Okay, how does that look? Can you see that now? This is now sharing the full screen rather than just the browser. Okay, I'm going to assume yes, but do ping me if you still can't see anything. Okay, so at the top of this notebook, we are installing all of the libraries. Now, you might think that this notebook was something that we could just knock up very quickly, but in fact, it's incredibly difficult to use all of this software. It's being developed at such a rate, and it's so new and so immature that it's really, really hard to, something as simple as attempting to pin libraries is impossible. I've got the Hugging Face Pest library at this point in time. It didn't have any versions. It didn't have any releases. I had to pin it to a specific commit in Git. And even then, you've got to try and find the perfect permutation where all of the stars align in these libraries and they all work together nicely. Because if you just change some of these numbers just by a small amount, it breaks something very, very hard to understand. So it doesn't. It's just bear in mind it's not easy to make this work. And yeah, bear in mind if you start sort of tinkering with this yourself. Lots of imports at the top. Right, let's talk about the model now. So the Falcon 7B is this model that I mentioned earlier, which was not necessarily a revolutionary architecture, but it's just been trained on a. Thank you for confirming that that's working now. Thanks, guys. So yeah, the model is a Falcon 7B. It was this model that has been trained on some clean data, and that's pretty much the only change. And it's kind of gained notoriety and performance purely just because of the good data in its data set. So that's the model. We're loading in the configuration to load everything in 4-bit mode. So 4-bit mode is kind of like you can choose between 8-bit, 4-bit, and I think soon 2-bit. 2-bit is pretty low, but apparently it works reasonably well. 4-bit is kind of like that elbow where it seems to work okay. We've then got we're loading the model up and the tokenizer. So yeah, remember the tokenizer is used during the training of the model, so you've got to be very careful to ensure that you're loading the right tokenizer, and so that's why generally it's part of the model. And yeah, that's all downloading. It's fairly big, it's tens of gigabytes in terms of download size. Once this actually goes into a GPU, it sort of fits in about like 8 gigabytes ish of GPU. And this is with the 7 billion parameter model. There are bigger models as well that you could try this with. So now I'm just writing some code to create some generations. Effectively the model.generate. This is using the transformers library, by the way. So the API, the interface is the transformers library, the model.generate, and these are the settings that you can use in order to change how it's generating. You got things like the different ways of sampling the generation. So you could use temperature, or in this case we're using like top K, top P sampling. Maximizing setting a maximum for the number of tokens that are generated, and yeah, and there we go. So what I'm going to try and do now is to attempt to get this model to generate a song, or generate some lyrics to a song. So the prompt here is just intro, and then I'm expecting it to generate some text there. There's a little bit of bad language there. Apologies, not me, it's the model. Then we've got the adapter config. So this is the low, it's the low rank adaption. The adapter that sits on the side of the model, and this is how you kind of specify the size and how big it is and stuff. This was just taken from an example, I think, from a Hugging Face blog post. So lots of scope for playing there. And now we get to the the custom part. So now imagine that you have your own data. This could be anything, remember. It could be proprietary data. It could be something from your internal company database. It could be PDFs or documents that you have on your internal wiki, anything like that. And what we're trying to do is we're trying to teach the LLM to be able to communicate in a way that befits your domain. That might be, it might be that there's new words that haven't really been represented or seen before. There's new concepts that haven't been seen before. There's new ideas or theories or types of customer, or so on and so forth. In this particular instance, I've found an example Beatles repository, or a list of text files that have Beatles lyrics in it. In the example that you can run, you won't have that text there. You'll have to pick your own data set, because obviously I don't own the rights to Beatles songs, so I don't want to distribute this, but I'm just using it as an example. And it looks a bit like this. It's just a load of raw text with intros, verses, and there you go. We need to do a lot of cleaning on this data, because it is really just presented like that. I spent quite a lot of time sort of figuring out how I wanted to structure it. And in the end, I kind of found that it was best to retain the structural information of the song. So basically keep the intro together, keep the chorus together, keep the verse together, and just present it as sort of one block of text. So that's what all this data cleaning stuff is doing here. And then finally, we can run our training code. So again, there's just this big helper, or couple of helper methods that the Transformers library provide to help us train this model. And I ran it on this data, and it took, with these particular settings for the adapter config and the quantization and the size of the data, it took about an hour, just over an hour, to train before it started to stabilize in terms of the training loss, which is one way of measuring how well the data has been incorporated. And then tarred up that final model, that trained, well, let's get a set of models now, I guess. I pickled it and tarred it all up, placed it into a tar file, and dumped it into my Google Drive. And then, fingers crossed, look at that. It's just got reconnected, disconnected. No way. Right, so I'm just going to quickly reconnect this runtime. Hopefully it will run. Yep, I'm connected. I'm pretty sure that we've lost everything now. Let's just, oh no, maybe not. Nice. It's still alive. Okay, so it's still cached. So we're all good. So this code is the inference code. This is a second file, and it's pulling the file from my that tar file of the finals Beetle, the final model that we trained. So reinstalling exactly the same prerequisites. Be very careful to install exactly the same prerequisites. Tag everything. And then we're just basically importing the same config with the same generate method, with the same sampling method. I mean, I guess technically you didn't need this last time. It was just for debugging. And then we can finally use it to actually generate some songs. But wouldn't it be great at this moment in time to have a song as well? Well, actually, we've just finished a project for Stability AI called Stable Audio. And this is a diffusion model, so a different type of AI model called a diffusion model that takes a bunch of text and it attempts to generate some real life music. So you might have seen like Stable Diffusion or Midjourney or other algorithms like that are generating images from text. Well, this is very similar, except that it's not generating images anymore, it's generating audio. So you can go to stableaudio.com and sign up, and there's quite a generous free tier where you can have a play with this, and you can type in some text and ask it to generate some music. So I'm just going to go ahead and do that. You can see all of the examples that have been generated in the past. I think the one that worked well for this for the purposes of this demo was probably the lo-fi hip hop beat rap type music, even though I'm not gonna attempt to rap because that would just be awful. Um, it's got a nice beat that'll work. So there you go. My one that I just ran a few seconds ago is just completed. It takes about 30 seconds to generate to create a generation, and it's all asynchronous. So, see that. Yeah, you see, we've got no beat to this one. It's warm and it's soft and it's hugged. Not great for a spoken song, though. So let's go back to this. I'm not sure how well you can hear it. You probably can't hear it very well at all, but that's okay. Imagine a lo-fi hip hop beat whilst I'm attempting to read out what our model has just generated. Oh, nice intro. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. Yahoo! I want to be your dog. Yahoo! I want to be your dog. Oh, I should just mention that I can't be held responsible for any of the words that are coming out of this LLM. And the band played on, and the people came, and they saw it was good, and they were satisfied. They were satisfied. I'll say the word. She says the word, and they'll understand. How long will it take till she sees the mistake, and so on and so forth. All right, so there's the one of the example songs there. Let's now try and make it a bit more topical, and I'm going to write a song about language models. This is a song about language models and the structures that they contain and the way that they repeat themselves and all the words that they surround. Oh, so close to a nice rhyme there. In a deep dive, you've learned how they work, and now you're part of the corporation. They'll take you in, screwed up or torn, solve all of your problems for a price or a song. Oh wow, that's depressing. But wait, the data presents another approach. You may observe the people passing by, and you'll soon realize that they're all living lives that are prescribed, and you'll see that they're all the same. And you know this is your language model. It's called Smoky Tongue. It can help you if you let it. It can help you if you let it. Next, you want to deploy the same old thing again. I've said it once, I've said it 100 times. It's no use, you'll never get it in your mind. And then the outro. I hope you enjoyed this talk, and I trust that you'll come again. The next time we'll talk, we'll have another tea and scone. Oh, nice. And goodbye for now. It's time to say goodbye. Goodbye. There you go. Not too bad. Interesting topic. I think, fundamentally here, we've only traded on a very small subset of data. Obviously, if you have a much larger corpus of songs, then it will just get better and better and better at rhyming. Rhyming is quite a high level concept, but I'm sure it could do it if you had enough data. All right, cracking. Let's just go back to the presentation again. Wasn't too embarrassing. Hopefully you didn't have to turn off your microphones. Yeah, final thoughts. So yeah, I'm going to publish this to the Winder AI blog. I'll put all the links and stuff in there. There's lots of links actually contained within the presentation as well. So I'll try and sort of paste them into the blog post, lots of links to papers and things. Of course, if you've got any questions, then you can reach out to me at phil@winder.ai. And of course, if you need any help with any of your projects, or if you know anybody that does need help with projects, then definitely reach out to us. That's our bread and butter. We love working on stuff like this. So yeah, check us out and let us know if you've got any issues that you'd like help with. All right, with that, I'll just pause there. I'm conscious that I haven't actually given you the GitHub link yet, so I'm going to go away and just find that for a few seconds and let some of the questions come in. I'm going to give me a second and I'll be back in just a minute to give you the link. I can't quite remember where I put it. Thought it was in the presentation, but clearly not. I'll get to the questions in just a moment. Nope, not that one. Oh, maybe I didn't do it actually. Can't find it. Okay, well, maybe let's leave that for a follow-up. Apologies, I thought I'd done it, but maybe I haven't even released it yet. So yeah, I'll make sure that that comes up on the blog post that emerges eventually. And in the meantime, yeah, let's have a look at some of these questions, shall we? Right. Um, yes. So you're asking copy the slides, at least the references. Yep, absolutely. I'll. I usually it takes me usually a day or two to kind of convert this to a video and then release it to the website. I'll send everybody a message to give you a link to that when it is done. Any useful links? Yep, same as before. All of the links are contained within the slides. I think there's even a few more actually. Talking a bit more of a background here, talking about some of the background and some more in-depth introductions to how GPT works. Okay, there's one more really technical question. Thank you very much for this. And this is a really tricky one, and I'm actually not going to attempt to answer it, I'm afraid. But what's the difference between PEFT and low rank adaptation? So they're both attempting to do the same thing, and no means an expert in the implementation details. But they're both effectively trying to do the same thing. They're trying to build a model that sits to the side of the main foundation model in order to make it easier to fine tune that model rather than the foundation model itself. The way in which they do that, though, it does differ slightly. The general consensus is that the word adapter is kind of encapsulates both approaches, but they do it in slightly different ways. I'm sure there's going to be other ways, better ways as well, that emerge in the future. And so I don't quite feel qualified to be able to give an in-depth definition or investigation of these two approaches and other potential approaches at this moment in time, I'm afraid. But that's a great question, and maybe that could be a future talk. Okay, and yeah, just a couple more questions asking about the presentation and useful links to share. Yeah, absolutely. I think the easiest way to do that is just after the fact. I'll release this to my to our blog, and the links will just be all clickable on there. There's a few more here though, if you do want to actually look it up. Okay, cool. So once again, thank you for bearing with me today. Apologies for the technical glitches, and at least the demo works. That's not common. Demos often fail, so that's great. This time it's the screen sharing that didn't work properly. But okay. Now that's another good question. One last final question just popped up before we go. Are there any guidelines for linking the number of fine-tuning examples, the amount of compute needed? Now, so that's a bit of a complicated question. So the amount of compute needed is defined by a number of things. So first, you've got the amount of RAM that you need to even load the model in the first place. Okay, so that could be GPU RAM. It's unlikely that you're going to attempt to fine-tune these models in CPU memory because they're just not fast enough, not efficient enough. So you pretty much need a GPU here. And that means that you need a setup that has enough GPU RAM to be able to fit the full foundation model plus the adapter model all in at the same time. Okay. Then you need to start streaming in the data as well, and that will need some RAM. But I mean, most of the frameworks are very efficient now in how they stream that data in, so it's typically a bit negligible. And then so that's RAM, fundamentally described by the size of the model, the number of parameters there. What about speed though? So in terms of speed, basically the better GPU, the faster GPU that you've got, the newer GPU that you've got, the better. That will work faster than older ones. And then we've got the linking the number of fine-tuning examples to the amount of compute. So the number of fine-tuning examples isn't really related to the compute. It's more related to how much data do you need to properly to properly internalize that information inside the model. And So that depends on the complexity of the model. If your adapter model is very complex, then you need lots of data. If it's very simple, then you don't need much data. And you need enough data to be able to represent all of the concepts that could possibly exist within that data. So it's largely, problem specific. All right. Hopefully that answers that question. And yeah, thanks for bearing with me. I'll see you again another time. Thanks a lot. Bye bye.